The error code H2 in air conditioning equipment does not have a single universal meaning. Each manufacturer may assign a different interpretation to this code depending on the type of system, the electronics used, and the design approach of the unit. However, in professional practice, certain behavior patterns and common meanings have been identified that help guide diagnostics based on accumulated field experience. Most frequent meanings of the H2 code: 1. Communication problems in multi-split systems. In multi-zone systems, the H2 code usually indicates a communication failure between the master unit, main outdoor unit, and one or more slave units in the system. In simple terms, the master controller detects that the number of connected units has decreased, or that one of them is not responding to the communication protocol. This scenario translates into desynchronization, which can affect the overall performance of the system or even shut it down for safety reasons. Technically, these failures are often due to loss of data bus integrity, noise, short circuits or interruptions, or errors in address configuration. This type of error is common in brands such as Midea, York, or Daikin, especially in multi-floor installations or with long cabling, where any connection issue can be amplified. 2. Failures in sensors or electronic boards. In brands like Haier or in Midea air-to-water heat pump units, the H2 code is linked to a faulty sensor. Usually this refers to the temperature sensor located on the discharge gas pipe, typically an NTC, although in other cases it may indicate an error in current sensors, pressure sensors, or the power supply sensor. When the sensor stops sending coherent information to the board, the microcontroller cannot adjust parameters such as fan speed, cooling cycle, or compressor protection, so it issues the H2 code to stop operation. Sometimes the problem is not in the sensor itself, but in the electronic board. Damaged components, carbonized traces, cold solder joints, or a faulty microprocessor may prevent the signal from reaching in proper conditions. It is recommended to visually inspect the PCB, look for swollen electrolytic capacitors, burnt resistors, or carbonized traces, and measure stabilized voltages to rule out failures in the power supply. 3. Dirty or defective electrostatic filter. In brands like Gree, the H2 code is associated with the condition of the internal electrostatic filter. These filters use plates or cells with high voltage to charge particles and facilitate their capture. Their proper operation depends both on mechanical integrity and on the high voltage power supply generated by the ionizer plates. These filters are designed to improve air quality by capturing very fine particles such as dust, pollen, or microscopic contaminants through an electrostatic field. Over time, they accumulate dirt and lose efficiency. When the filter is saturated with dust or deteriorated, airflow resistance increases, ionization capacity decreases, and the system interprets this as a malfunction, generating the H2 code as a warning to perform cleaning or replacement. In addition to dust accumulation, it is common to find plates with carbonization due to partial discharges, oxidized power contacts of the HV generator, or ionizer wires with intermittent continuity. In such cases, cleaning alone is not enough. It is necessary to verify the voltage of the HV generator following safe high-voltage procedures, and the mechanical condition of the plates. Common causes. Communication interruption. The failure may originate from faulty wiring, loose connections, poorly made splices, external electrical noise coming from nearby motors or variable frequency drives, or even intermittent power cuts in one of the units. Checking the integrity of the twisted pair, shielding, and low-frequency continuity is the first step. Defective electronic boards. The electronic board of the master unit or a slave unit may show burnt components, swollen capacitors, cold solder joints, or general malfunctions that cause loss of communication or misinterpretation of signals. Measuring reference voltages and checking DC to DC converters, regulators, and MOSFETs helps locate the failure. Configuration problems. In multi-split systems, if addresses are incorrectly assigned, duplicated, or inconsistent with the manufacturer's design, the master controller cannot recognize them properly, causing the H2 error. Checking the address table, dip switches, or software configuration is essential. In addition, errors in startup order or group tables may simulate communication failures. Unstable power supply. Low, unstable supply voltage or voltage spikes can affect sensors, boards, and control logic, triggering the code. This is common in regions with unstable electrical networks. Measuring voltage between phases and ground, checking for harmonics and transient spikes, and, if necessary, installing surge suppressors or stabilizers reduces the likelihood of repeated failures. Damaged or disconnected sensors. An open, short-circuited temperature sensor, one with out-of-range resistance or with corroded wires, can generate incoherent readings and trigger the error. Connections in humid environments can corrode. Using a test kit with known resistors allows for faster verification. Saturated electrostatic filters. Excessive dust, grease, or contaminants increases the electrical resistance of the electrostatic filter, affecting its function and causing the equipment to trigger the error code. Additionally, accumulation may cause leakage points or arcs that damage the HV generator. Solutions and technical procedures. 1. Communication in multi-split systems. Check and tighten all communication and power wiring between units. Inspect splices and terminals for corrosion or mechanical stress. Ensure there are no external electromagnetic interferences. If variable frequency drives, large motors, or RF sources are nearby, relocate cables or add filters or ferrites. Verify that all units are powered on and correctly addressed. DIP, jumpers, or software. Document the address map and compare it with the original design. Inspect electronic boards for burnt components or damaged traces. Replace if necessary. If available, use an oscilloscope to capture data frames and check integrity, noise, or corrupted frames. If the architecture allows, isolate units by sections, physically disconnecting a line to identify the unit causing the disturbance. 2. Problems in sensors or boards. Measure the resistance of temperature probes, generally NTC type, with a multimeter in the kiloohm range. Compare with the manufacturer's curve or table. For example, many NTCs are 10 kiloohms at 25 degrees Celsius. If the equipment manual is not available, observe whether resistance decreases when rubbing the sensor with your hand. If the sensor's resistance value is known, it can be simulated with an equivalent resistor to check the board's response. Verify continuity, connector conditions, and wiring. Check that there is no high contact resistance at terminals that could distort readings. Replace the temperature probe if it is out of range, open circuit, or short circuit. Before replacing, clean contacts and test with a resistor bridge to confirm the fault comes from the probe and not from the PCB input. If the probe is correct, inspect electrolytic capacitors, MOSFETs, diodes, and fuses on the board. Measure supply voltages with the sensor connected to the board. The direct current voltage reading should be very close to 2.5 volts.